So looking at page 83, set up an integrated, I can't even talk anymore. It says it right there. Set up an iterated integral for the volume of the region bounded by the cone and the sphere below. All right. So on the previous page, we had different situations that involved, bottom line, you were given an integral to work off. If you're given nothing. All right. You can go back and look for something that's similar. You find some cases that kind of feel a little bit along those lines, maybe one of these problems, but it's not going to really do you any good because they weren't tailor-made for spherical coordinates. This one is. All right. So the iterated integral to find the volume has to capture that little ice cream cone in the middle. So let's focus on the diagram first before we can do anything else. All right. And that becomes the key thing when it comes to spherical coordinates. Now, it's not like the end all in terms of rules. Oh, that's pretty. It's not the end all in terms of rules, but there's a good place to start. Analyze the diagram and see what's going on there. All right. So I see that I have an intersection here. All right. Now that intersection isn't just localized to these 2 points. It's everywhere along this ring, which, without looking at any equations that they provided on the side, without looking at any of that stuff, I suspect that it's either a circle or it's an ellipse. That doesn't really narrow it down though. All right, but my suspicion is that it's a circle, just because we're dealing with what looks like a sphere intersecting a cone. And, my artwork aside, it does look to be symmetrical. So I have no reason to doubt that it would be at least somewhat circular, and if not just flat out a circle. All right. So what I want to do is capture all the volume within this figure, but I also need the cap. I need the ice cream on the cone. All right. So I need this also. All right. So I need the top to the whole thing. All right. So we got this appears to be some sort of a cross section intersection. And then we have a cover for the whole thing. All right. So we have a volume contained within the cone. Now, if that cone extended without bound, it would just be a matter of saying, all right, let's go to spherical coordinates, because the spherical coordinates uses the z-axis as a basis. All right. So it starts off with the z-axis, sweeps out from there, and then rotates or revolves around the z-axis. So instead of thinking XY plane up, we're thinking z-axis out. All right. So we could get all this just from looking at that, the cone and spherical coordinates. All right. As far as the sphere is concerned, though, it's a little bit of a different story. And in fact, it's really up to you, because you might look at it and say, well, I think I stand a better chance of evaluating the sphere, the hemisphere part of it, with cylindrical coordinates, for example, or rectangular coordinates, but the cone, I want to work with spherical coordinates. There's nothing wrong with that. All right. But it does seem like this is going to come down to our ability to define that intersection between the two, just to at least know what the extent is of this angular movement. All right, we know it starts off at 0 in terms of phi. Get a brighter color there. All right, we know it starts off at 0 in terms of phi, but we don't know what the extent is. We don't know how far out it's going to go. All right, so we would want to figure out what this angle is. We know it's going all the way around. So if we're looking on the XY plane, if I start here, now I want to go to the darker color. If I start here and work my way around in terms of theta, that's going to be a 2 pi movement. So 0 to 2 pi. All right. So I'm good on the theta part of it. It's just a question of the rho now and how the rho is going to play into it, and whether I need multiple integrals or a single integral. You know, if there are multiple integrals, can they be combined into a single integral? But it does seem that it's all going to come down to our ability to cap it off based off of that sphere equation. But a good place to start would be to set these two things equal to one another, because that would show an intersection. All right. Now we can do that in spherical coordinates. We can do it in rectangular coordinates and see where it takes us. You know, a good first step would be, you know, just look at each one of them individually, maybe, and then go from there. You know, so z is equal to the square root 3 times x squared plus y squared. Now, if we were going to cylindrical, we'd call that r squared, but we're not. We're looking at spherical coordinates. The other z, if we factor out a -1 here, we could say 4 minus x squared plus y squared might be helpful. All right. Now, if I want to set these two equal to one another to see where they intersect, I could do that pretty easily. All right. So let me just I'll duplicate them and then just move them around. All right. So you square both sides, 3 parentheses x squared plus y squared is equal to 4 minus x squared plus y squared. Lost the closed parentheses over here, so let me take care of that. All right. Got a common factor if we bring it all together. That's a possibility. I mean, we could also do a substitution if we want. I mean, there's so many different ways to go about this. But let me just consolidate at least at first. At least at first. That was brilliant. Right. So at least first, let me consolidate. At least 3 x squared plus y squared plus, I'll call it 1y squared, 1x squared plus y squared equals 4. Because we have like terms now, we can put it all together and get 4 x squared plus y squared is equal to 4. And now we have x squared plus y squared is equal to 1. I mean, that's a circle equation in rectangular coordinates. All right. Now we want polar coordinates. So I'm going to keep our eye on the prize here. But that's good news. So looking at this puppy right here, that's a relationship between x squared, y squared, and something in terms of polar coordinates. Right? So I'll make that adjustment here. This is really just going to be, if I make the substitution here, instead of rho sine phi, it's going to be rho sine phi squared. All right, rho sine phi squared. All right. So we can work off that. That gives us a relation. I mean, when you take the square root of both sides, you know, it's not very often that you're able to say, let me take the square root of both sides and something that's a power of 2, like as in the case of x squared plus y squared, where in rectangular coordinates, you wouldn't be able to take the square root of both sides and actually get something relatively clean. In this case, you actually can and do, you know. The other way to do it would be to slap a radical over both parts. You know, you can do this, in which case you get what we're about to get, which is rho sine phi is equal to 1. All right. So we have a relation between rho and phi. And that's good. That's information. All right, we could look at each one of these equations individually, and we have to, because if we're gonna be able to find the volume captured within each one of these, that's going to be an important piece. Right, so we can look at those individually and say, for example, Z, take this guy. So we're in fact finding mode right now. Z is equal to the square root of 3, blah, blah, blah. Well, we know Z over here by definition in spherical coordinates is rho cosine phi. Dang it. All right. Now the radical x squared plus y squared, that part of it, if I split this up, could be thought of as radical 3 times radical x squared plus y. That could be thought of as rho sine phi. So we have rho cosine phi equals radical 3 sine phi. And it's like, oh, we're going nowhere in a hurry here. But there's two things. One, depending on what we're looking for, and just keep your mind on the fact that we're trying to figure out what phi is. All right. So anything that's going to help us simplify this is going to be useful. So there's two things that we know. One, at the phi that we care about, rho sine of phi is equal to 1. So I have a substitution that I could use. All right, rho sine of phi is equal to 1, in which case I would be looking at rho cosine of phi is equal to radical 3. All right, so I could do that. That would be helpful, I guess, but it's still an equation with two variables. Another thing I could do is consolidate the sine and the cosine with one another so that they, excuse me, so that they become a tangent. All right. So if I divide both sides, let me get a red back into the party here. So if I divide both sides by rho cosine phi, rho cosine phi, we can get the rows to cancel out. And on the left-hand side, also the cosines, we'd be looking at 1 over rad, it will be 1 over rad 3, times the sine of phi. So 1 equals radical 3 sine of phi. It becomes 1 over radical 3 is equal to, and I said sine for whatever reason. I'm just making stuff up now. Tangent of phi was the whole point. All right. And since the whole objective here was to figure out what the value of tangent would, the value phi would be, not the value of tangent, we're on the right path here. So tangent, inverse tangent, but I'll say phi is equal to inverse tangent of 1 over root 3, which is pi over 6 or 30 degrees or whatever. You know, if you don't know it, you just put it into Desmos. All right, so inverse tangent 1 over the square root of 3. You get that number in radians. But then if you kick it over into degrees, you see that it's 30 degrees. But make sure you put it back to radians, because that's more useful for it, more better. All right. So then if I'm looking for the rho value, for example, and we do need to know the extent of this in terms of rho, although common sense tells us based on the fact that they very nicely labeled the graph for us, but they very easily might not have. It's a good thing that we have this computation here that has a rho and a sine of phi involved, because I now know what the extent is of phi. So rho sine pi over 6, rho times 1/2 is going to give us rho equals 2. But like I said, they gave us the z-intercept, so we kind of knew that, but it's the way of verifying it. So we know the furthest extent for rho, and we know the furthest extent for p. We also know theta is going from 0 to 2 pi, right? So we just got to make sure that what we're capturing here is a volume in the spherical sense, right? So we're saying that if we visualize this, that rho is going to go, it's going to start off at on the z-axis, but it's going to start off also at 0 in terms of really everything except for z. 0 for phi, 0 for theta, and all that. All right. But its z value is equal to 2, which corresponds to a rho value being equal to 2. All right. Still too dull. All right. That's getting swept through an angle of pi over 6. All right. So that measures pi over 6 radians. And then the whole thing is getting swept around the axis, creating this cone-shaped figure, but like cone-shaped in the sense of an ice cream cone, right? So those bounds will get the job done. We just have to set up our triple integral, right? So triple integral, rho squared sine phi, d rho d phi d theta, going from 0 to 2, 0 to pi over 6 for phi, and 0 to 2 pi for theta. So I think the moral of the story here is be patient with your bounds, but if you are, there's a reward in it for you because you get a much simpler triple integral to work with. All right. Yeah, close enough. So that's really it, because it's much simpler when you're dealing with something that's tailor-made for a spherical coordinate system. It's much simpler to actually use the spherical coordinate system. If I had tried to do this with rectangular coordinate systems, or rectangular or even cylindrical, it'd be here for a whole lot longer. All right, but you got to do the work to get the bounds. All right, that's really all it comes down to. And a good visualization of what's going on is really tantamount to success. All right, so thank you, word of the day. So anyway, stop recording.